Here we are, it's the physics video lecture once again. Fluid mechanics video lecture 7. Okay, got some really great stuff today. I'm going to begin by writing out our entire list of equations and results that we have so far. So this is ideal fluids and potential flows. So ideal fluids, and we're getting to the potential flows this time. And we begin just with listing all of our equations. So results, and they'll fit here on this board. Okay. So what do we have? We have continuity equation. We've done a little bit with that. We will be using it some more. That's a continuity equation. The entropy equation we have not used yet. We'll make use of it in a very simple manner, but we'll put it up here for the record. V dot gradient of S equals 0. And this, of course, just means that the entropy is constant along the fluid flow. Then we have, then we have Euler's equation that we've made great use of so far. So dV dt plus V dot gradient equals minus gradient of the enthalpy, and of course, or minus gradient P over rho plus G if we need that form. This is coming in handy for us. Now there was an equivalent formulation of this that I'm going to write down. There are a couple, I only need one of them. Yeah, we have or dV dt minus this curl of V. No, V cross curl of V, sorry, minus V cross curl of V. And then we have the minus gradient of W plus V squared over 2. Okay, I thought this was all going to fit on one board, but that's all right. So for the moment, Euler's equation we've done quite a bit with, because first of all, we got our fluid statics out of it. We did the rotating bucket with it, and we used it to generate Bernoulli's equation as well. So I'll continue on the other board, I believe. Yeah. Just to have everything up here. Streamlines. So we'll make use of all of these things. This was the dx over bx, dy over vy, dz over dz, which just simply defines a streamline. And we had Bernoulli. I'll put it in the form so if we have long streamlines, we would have Bernoulli's equation, P plus 1/2 rho V squared, and if you have gravity gradient, rho Gy equals constant. In addition to that, we have the circulation and that was this line integral V dot VL. Of course, that could be boundary of an area. Curl of V dot D area equals constant. So along a stream, flow along a streamline, you have this being constant, which is especially interesting in terms of the curl of V. And then we have if curl of V equals 0, then simply by the Helmholtz theorem, V is equal to the gradient of a potential and this is what we're going to continue on with. And in fact, and what we really ended up with last time, an example flows that are due to small oscillations, okay? I'll just write small oscillations, then we have the curl of V vanishing, okay? So this is what we're going to talk about now, are these potential flows. We had sort of formal examples of them, but they kind of break down in a certain sense in reality. But the small oscillations is one that we're going to take all the way. Good, so here we are now talking about potential flows. And I have everything up on the board, and I'm going to use this equation here. Let's do like we do and call it star. Equation star is this one. So for potential flows now, so now suppose we have, for whatever reason, V is equal to the gradient of phi of x, y, z, and t. Okay. Then we immediately have, we're up here in equation star, we immediately have the curl of V vanishing, and we have dv dt equals minus gradient w plus v squared over 2. Of course, we know we can go in with that as well if we need to. Okay, so I'm going to just take my gradient into here and exchange the order of differentiation. So now we have, with our equation star, the gradient of d phi dt, and bringing the right side over, plus w plus d squared over 2 is equal to 0. And from this, since these are the spatial derivatives, we can conclude that the argument here, the expression of the parentheses, is a function of time. So now we have d phi dt plus v squared over 2 w is some function of time. We're never going to have to actually know what this function of time is. When we make use of this formula, we can imagine that it's absorbed into phi itself, right? So you imagine the antiderivative of this is absorbed into phi, and the time derivative just takes care of it. But what we do have, if phi is not explicitly a function of time, then we have v squared over 2 plus enthalpy equals constant. In other words, that, or we can of course go in with this expression here, gradient p over rho plus g instead of that. So yeah, what we get is Bernoulli's equation. We immediately have Bernoulli's equation. But not just along a streamline, but in fact in the bulk, okay? Because we don't have the restriction that we're on along a streamline here. What our restriction this time is that it is a curl-free field. Remember, curl gradient or curl of gradient vanishes identically. That's why we got rid of that term right there. So we get Bernoulli's equation, and we can take that one more step. So we get Bernoulli's equation, everything we've already learned about Bernoulli's equation. But remember, the pressure is in here as well via this expression here. So I'll go ahead and write P plus 1/2 rho V squared plus, say, rho GY equals constant, you know, in that general form. And yeah, what we're going to do now is take it one step beyond this. So we have V is equal to a gradient of phi. Now you may remember, where are we? In Euler's equation, we had known that when rho is constant in compressible fluid, we have divergence of V equals 0. And then what we're going to have is div grad phi is equal to 0. Okay, so then all of potential theory can actually be applied now to fluid mechanics. So that's what I'm going to write up here next. So this is ideal fluids, potential flows, and now incompressible fluids. So we're just continuing this discussion here. If the fluid is incompressible, then divergence of V equals 0, which is a divergence of the gradient of phi is equal to 0. So we say we have del squared of phi is equal to 0. Okay, Laplace's equation. Okay, that's so major that we'll go ahead and put a red box around it. The boundary conditions were that V dot n hat, which we see now is going to be gradient of phi dot n hat equals 0 at a fixed boundary, at a solved boundary. And we still have this. We actually have this for our pressure. And if you want to get the pressure, you have d phi dt plus everything that's in there. P plus b squared over 2 equals 0, or equals f of t for the moment. We'll never need the f of t equals constant to get the pressure. So good, let's see if that's what I wanted to write here. Not quite, P over rho. And I think I can just say it's a constant, right? Yeah. So d phi dt plus P over rho plus V squared equals constant. That should be the form. Just make sure that that is the form. Yeah. Okay, good. V squared over 2. And you know, if you need the rho gy, that can also be built in there. Okay. So there is the thing we're going to work with now. Now there's a whole theory of potential theory that we just want to have a little look at to illustrate some of the stuff I had said. But yeah, this is your complete problem now. Incompressible fluid, solve Laplace's equation, you've got your boundary condition, and if you want to get the pressure, essentially you're getting the pressure by solving for V, you know, getting V out of this equation, and then you go into here and find the pressure, okay? So, let me set something up. Good. Okay, any vocabularies for us up there? Got Miller's equation, got Laplace's equation. Yeah. Okay. So here's our example. This is something you'll find all over the place. I just worked through it a little while ago, and I'll give you the outlines of it. So we're looking for the two-dimensional flow as described last time around a cylinder. And you know, we'll take this as our origin. This is a cylinder of radius r. And the flow, we'll do it in blue. We're just going to indicate the symmetry here. So we're coming in from far away. We're going to get these flow lines. And we're going to use plane polar coordinates. So as you guys remember, we'd have r hat pointing this way. If this is our angle theta, and we would have theta hat pointing that way. And at any point here, for example, here, just supposing that that's what we have, streamlines, then we would have V in plane polar coordinates. So in plane polar coordinates, we would have V equals V sub r times r hat plus V sub theta times theta hat. And yeah, if you have to solve a problem with this symmetry, with this fixed boundary here, I could just shade a little here. Okay, this is fixed. 2D flow. Then you're going to have to use plane polar coordinates. Good. So what do we have? Del squared phi. So we need the Laplacian in 2 dimensions. So let me put the important stuff here. So 1 over r d over dr r d phi dr plus 1 over r squared del squared phi d theta squared equals 0. So that's our equation. It's a very standard material. What you can do is let phi equal f of r g of theta. You go into that, you separate variables. You will find differential equation in r and in theta. They're both equal to the same negative constant. And the one in theta is just going to turn into e to the I theta, or e to the I n theta. And this one will be a little more involved. So I'm going to write down what you get. You get phi of r and theta equals u times r plus r squared over r times cosine of theta. This is one part of an infinite series that you would get, but it's the part that will satisfy the boundary condition. Because this one has to satisfy so this, I'll just write here, satisfies v sub r equals d phi dr equals 0 at r equals capital R. So yeah, you can test these things out, no problem. At some point you'll actually, in some class, you'll actually generate all of these functions here because that's very standard material for this kind of symmetry, for example, in electricity and magnetism. Okay, what do we want to do? Discuss this a bit. So I'll write down there, I'm going to erase this now. Let's see what we're going to get out of this. Okay, this one satisfies the boundary conditions. So we have v sub r is equal to d phi dr. V sub phi, 1 over r d phi d theta. Yes, 1 over r d phi d theta. So let's write those down. D phi dr, we're just going to have a 1 and a minus r squared over lowercase r squared. So d phi dr is equal to u 1 minus r squared over r squared cos theta. Oh, and I should say this speed u here is the speed out at infinity. So these streamlines way out here, that's the speed out at infinity. Minus infinity and plus infinity. Good, so we have that. Now what about v sub, that's not a phi anyway, it's theta. How many times did I do that? Oh, we're good, v sub theta. So 1 over r, d phi d theta, again we're going to have 1 plus r squared over r squared. So this time a positive sign, u 1 plus r squared over r squared, like that, minus sine theta, and a minus sign. Okay. Good, so that's our v sub theta, and what we want to do is make sense of it up here. Okay. And that's something you guys play around with. Note v sub theta evaluated at r equals capital R. We already saw v sub r here is 0 because lowercase equals uppercase, 1 minus 1 is 0. V sub theta, we're going to have minus u 1 plus 1, so times 2 times the sine of theta. So how's that working with this minus sign? Well, remember, we have to go up to this thing here. I will do this in red. It's a nice example. Suppose we are, well, first of all, this point. Yeah. So V sub, so on the surface, right? On the fixed surface there, V itself, right? V sub r is 0, so it's just going to be V sub theta r equals r times theta hat. So let's see what we got here. We got minus 2u sine theta minus 2u sine theta hat. So I could probably just do this by pointing. Theta hat, let's for example just take, well, anywhere on the surface, you know, your theta hat is like this on the surface. And so the minus sign is just what we needed, okay? Because it's gonna, because the direction, of course, we're coming in from the left, so the direction is opposite those little red arrows. And also you see we have a substantial fluid flow on the surface. In fact, up at the top there, it's twice the speed at infinity. And then, you know, it decreases down to 0 exactly at theta equals 0 and theta equals pi. So the whole discussion we had last time about D'Alembert's paradox, that's, you know, explicitly seen here with the pressure distribution. So as far as the, yeah, I should write one more thing down here. But yeah, we see first of all that we have finite speed, so the streamlines exist at the surface. Okay. So on the surface we have this. There's a discussion of the, you know, note the direction of theta hat. We just talked about it. Also, now if you wanted to go in Bernoulli's equation to get the pressure, you'd need V squared. But V squared is easy to get because r hat and theta hat, you guys remember, are perpendicular. So it's just VR squared plus V theta squared. And that's as much as we're going to write. We would have to, you know, square these things out, so it's not that beautiful. But it's also not impossible to do. Okay. And yeah, you'll have that symmetric pressure distribution along the surface. It's clear that there's no resistance to the flow, and that's not strictly physical, to say the least. So even though a lot of, you know, this is really important, and you can look up all manner of treatments of this thing. But it's important for us to realize that, you know, that it's not physical, and you'd have to treat a solution like this with care. Okay. Okay. So let me see. I think that's what I had to say about this example here. Yeah, if you wanted to, you know, you could leave a lot of room here. If you wanted to, you could look up the divergence operator. Find the divergence operator for plane polar coordinates, or for cylindrical coordinates, just use 2. And then you could test the solution for divergence vanishing. Curl, you'll see curl vanishes trivially. So that's all completely legit here. Anything else? Okay, that's good. Let's consult the clock here. Yeah. So there's one more treatment I want to do of this very scenario, and that is to tie this two-dimensional flow and Laplace's equation. Where do we have it? Right there. into some complex analysis, in particular the Cauchy-Riemann equations. So there are techniques in complex analysis that allow one to solve all manner of Laplace's equation type of problems. So that's worth mentioning as well. I will reproduce that picture. Yeah, I'll start with a new one, same thing. So what we just did, we actually have the full solution. We can, discover anything you can discover about this problem with what we have on the board. Now let's look at it again under a slightly different aspect. I'll just say we have R here. You could say we know these streamlines now, or we could if we had some patience. And in particular, there will be streamlines that actually touch the surface here. I don't want to get any more explicit than that. Okay, so what about streamlines? So let's call this streamlines. And we obviously had X and Y coordinates like that when we did our plane polars. So streamlines and 2D Laplace's equation. So let's look at the streamlines. We have dx over vx equals dy over vy. That means dy dx minus vx dy is equal to 0. Okay, so that's a relation that holds true for the streamlines. Another relation is that suppose c of x and y equals a constant along the streamlines. Right? You'd have a function in x and y, and setting it equal to a constant, implicitly defines a streamline, or a function y of x, say. Okay. So suppose we have that, then deep C is equal to deep C dx plus deep C dy equals 0 along a streamline. Okay. So again, this thing is here is along a streamline. So yeah, we can compare these two situations, okay? Vy dx minus vx dy. So then, third point here, what would we get if we compare those two? So we would say Vy must be equal to deep C dx, then Vy would be deep C dx, and dx would be minus d c dy. But fourth of all, we already have d phi dy, right? Because v is equal to the gradient of phi. because we're doing 2D Laplace equation, or because we have a velocity potential. So what do we have here? d phi dy is equal to dc dx, and d phi dx is equal to minus dc dy. Well, at this point, we're looking at the Cauchy-Riemann equations. This looks just like the Cauchy-Riemann equations of complex analysis. And in fact, both of these functions, phi and c, will satisfy Laplace's equation, because if you do d squared phi dy squared plus d squared phi dx squared, you'll just get these mixed partials, one with a minus sign in front of it, add up to 0. So Cauchy-Riemann equations and del squared phi equals 0 we already had. Del squared c is equal to 0. Okay. So that's pretty interesting. And it allows you to just set up really any differentiable complex function, because a differentiable complex function automatically satisfies the Cauchy-Riemann equations. So any differentiable complex function can be thought of as a solution to this scenario. And then you have to find out what is it the solution of. So you could have simple formulas like f of z equals x plus iy, and that would actually represent a solution to a flow problem. You can then go there and interpret it and see what it actually means. But yeah, that's what we have because of this. Let me wrap that up, because we're not actually going to practice this, but I want to make the connection to you guys clear that it's there, and that there's a whole world of two-dimensional flow problems that can be tackled with complex methods. Okay? Complex methods of solving Laplace's equation, as I wrote right up there. Okay, so I'm just going to make sure I've got a reasonably complete discussion here. Oh yeah, I did miss one point. Good. For this stream function here, which is c. So yeah, let's label this stream function. It's constant along a streamline, and you can set things up so that it vanishes at the surface. That's a constant equals 0. Anything else? Well, I'm just going to open up a little board, whatever I find here to round out this discussion, I'll put right here in this square. See what I have here. Got the Cauchy-Riemann conditions. We're not going to pursue that too much further. Okay, so this thing is constant along the streamlines. Oh, that's the other thing. So if you can find a function that's constant along the streamlines, and then you can use the Cauchy-Riemann equations to find phi, right? So if you can find c first, these two equations allow you to find phi integrated up, and that phi is, of course, the actual velocity potential, which gets you the velocity. Okay, we'll leave it at that. And next time, so we'll leave these ideal flows that are very famous and formally very important, and they're useful. Bernoulli's equation is very useful, but I just want to stress this condition of a fluid just streaming along the surface and having a tangential component is not physical, and that's why a very slow fluid flow can look like this, right? But as soon as the speed picks up a bit, all these eddies are going to detach and you're going to get turbulence downstream. Still a problem that needs to be solved, by the way. Okay. So yeah, the ideal case is primarily, it's not even primarily useful for low speeds and also for flows when you're sufficiently far away from those fixed surfaces. So what are we going to do next? We're still going to be doing potential flows, but the application will be sound waves and water waves. So we'll use the potential formalism to deal with sound and to deal with waves on the surface, surface waves. So surface. Okay, so that's a great subject too. We'll leave it at that. See you guys next time.